Hello, today I'm going to go through the solutions to the workbook on growing quadratic patterns. So the first pattern we start with is this pattern. And what I'm going to try to do is attempt to draw the general term in the pattern, so the nth term. So if you think that this is term 1, term 2, term 3, I'm trying to find the nth term. What would that look like? So I'm just going to do it visually first of all. So the first one we're looking at, we can see this is a 1 square plus 1 more. Here we have a 2 square plus 2 more. So if I just draw it in like, sorry, a 2 square plus 2 more. You should be able to see that this one is a 3 square plus 3 more. So our nth term should be an n square plus n more, or our general term is n squared plus n more. Okay, so that's how you would do this pattern visually. Let's now look at it algebraically. So what we need to do is create a table with our 3 terms in it. So we have 3 terms. And what we want to do is count the number of squares in each term. So here in our first term we have 2. In our second term we have 2 times 3 is 6. In our third term we have 3 times 4 is 12. Then we look at the first difference. So 2 to 6 is plus 4, 6 to 12 is plus 6. So it's not constant, so at least we know that it's not linear. We can actually tell it's quadratic because we've got rectangles going on here, and every time you have rectangles you're talking about quadratic. So now we look at the second difference. So to go from 4 to 6, we're adding 2. And we recall that in a quadratic, the second difference is also always equal to 2 times a, where our general term is written in the form an squared plus bn plus c. So if 2 must be 2a, that implies that a is actually 1. And we can substitute that in over here. So our general term is n squared plus bn plus c. And we still need to find out what b and c are. So let's go to our first term. So our first term happens to be the number 2 here. There's 2 squares in our first term. But if we take 1 and substitute it into our formula here instead of n, then we also get this first term. So if we substitute 1 in, we'll get 1 squared plus b times 1 plus c. Or we'll get 2 is equal to 1 plus bc, which implies 1 is equal to b plus c. So we do the same with our second term, term 2. So term 2 is 6. And if we substitute 2 into our general formula, we'll have 2 squared plus 2b's plus c. So 2 squared is 4, 6 take away 4 is 2, so that implies 2 is equal to 2b plus c. So we have a set of simultaneous equations here that we can solve. I'm going to subtract one from the other. So 2 take away 1 is 1, 2b take away b is 1b, and c take away c, it's eliminated. So b is 1, and I can see that I've got 1 is equal to 1 plus something, that something must be 0, so that implies c is 0. So now I know my general term is n squared plus bn is 1n plus c is 0. Turning to the visual representation, we saw a few moments ago that we could view this pattern like this with a square and something added, a square and a constant added, a number added, a square and a number added. So that was one way we could look at this pattern. There is an alternative way to look at the pattern. If we consider it as a rectangle and we consider that it is multiplication. So if we look at the first rectangle in our pattern, we have its side here is length 1, but here it's length 2. And that's our first term. Our second term, its height now is 2, but its length has increased to 3. And our third pattern, its height now is 3, and its length has increased to 4. So our general term then, our nth one, our nth pattern, we would expect that its height would match the term number. So our nth term, its height is going to be n, and its width here is going to be 1 more than the term number. So 1 more. So along the length here, we're actually going to have length n plus 1. So internally, the number of squares that we have internally, this is 1 times 2, this is 2 times 3, this is 3 times 4, so this one is going to be n times n plus 1. And if we multiply out the brackets, we'll get n squared plus n, same as before for our general term. This is the next pattern to be looking at. So if we consider this pattern, using that method that we used a moment ago, we were looking at the stage numbers. We've got 3 stages visible. We look at the height of the rectangle. So this one is height 3 and length 4. This one is height 4 and length 5. This one is 3, 4, 5, and 1, 2, 3, 4, 5, 6. Okay, so we can see each time that the height is 2 more than the term number. So we would expect our general term, our nth term, to have a height which is 2 higher than n, or n plus 2. And we expect the width to be 3 more than the term number. So 3 more than n is going to be n plus 3. So this is actually n plus 2 multiplied by n plus 3 will give you your nth term, or your general term. If you multiply that out, you have your general term is n squared plus 5n plus 6. Okay, and just to see that visually, that's what this pattern is showing you. This is the same pattern, repeated. Okay, and if you look at the length of this side, it's 1 plus 3 more, 2 plus 3 more, 3 plus 3 more, and then the height is 1 plus 2 more, 2 plus 2 more, 3 plus 2 more, which is what we were coming up with. The height is plus 2 more, the width is plus 3 more. But we can also see here that we have a 1 square, a 2 square, a 3 square, so we'd expect an n square. And then we have 6 yellow squares each time, so we have our 6. And then we have 3, 4, 5 ones. Here we have 3, 4, 5 twos. Here we have 3, 4, 5 threes. So we have 5 n's each time. the next pattern to consider. If we look at the width of the rectangle, in each case, we can see that the width here is 1 plus 2 more, 2 plus 2 more, 3 plus 2 more, 4 plus 2 more. So our general term is going to have width n plus 2 more. And its height then is going to be, that's 2 plus 3 more. This is 2 2's plus 3 more. This is 2 of these 3's plus 3 more. This is 2 of the 4's plus 3 more. So we're going to have 2 of our n's, so we'll have n and another n and 3 more, or 2n plus 3 more. So our general term is going to be n plus 2 multiplied by 2n's plus 3 more. We're going to have 2n squareds and 3n and 4n and 6. 2n squareds plus 7n plus 6. So we should be able to see that in our pattern. Say for example on this fourth term, we have 2 of our squares. We have 7 4's. We have 1, 2, 3, 4, 5, 6, 7. And then we have 6 yellow squares left at the end. If we look at our third term, we have 2 squares. And then we're counting 3's, so we should have 7 3's with 1, 2, 3, 4, 5, 6, 7, and we have 6 more. In this pattern, we're actually seeing a rectangle with a bit removed and a square, or a square and a rectangle with a bit removed, a square and a rectangle with a bit removed. If we look closely at the rectangle, it actually consists of a square and a rectangle, a square and a rectangle, a square and a rectangle. So what we could expect to happen is we've got to come from a 1 square, 2 square to 3 square, so we're expecting our n square. One square, 2 square, 3 square, n square. Our rectangle here has 5 1's. Here we've got 5 2's. Here we've got 5 3's. So here we might expect 5 n's, or 5n. But each time 3 have been removed. So we need to remove 3 at the end. So our overall general term is going to be 2n squareds plus 5n, but take 3 away. Solving this particular one algebraically. We set up our table with our 3 terms. Our first term has 4 squares in it. Our second term has 15. And our third term has 30. So our first difference is plus 11 and then plus 15, and our second difference is plus 4. So our general term is going to be an squared plus bn plus c, where we know already that 4 is equal to 2a, so that implies a must be 2. So if we substitute that in here, we've got 2n squared plus bn plus c as our general term, and we still need to figure out what b and c are. So if we look to our first term, term 1 is 4, and 4 is going to equal 2 times 1 squared plus b times 1 plus c, substituting in 1 into our general formula. So 4 is 2 plus b plus c, or 2 is b plus c. Do the same with our second term. Second term is 15. And 15 is equal to 2 times 2 squared plus b times 2 plus c. 15 is 8 plus 2b plus c, or 7 is 2b plus c. I'm going to subtract these two equations. So 7 take away 2 is 5. 2b take away b is b. C take away c is 0. So b must be 5. And that will imply that c is actually minus 3. So our general term, Tn, is 2n squared plus 5b's, take away 3. Our 2 squares plus our 5 times our n, take away the 3 each time. This is probably the easiest of all the quadratic patterns that we're looking at. So we can see our first term is 1, which is 1 squared. Our second term is 4, which is 2 squared. Our third term is 9, which is 3 squared. So our nth term will be n squared. Again, this one's quite simple. We have 4, which is 2 squared, 9, which is 3 squared, 16, which is 4 squared. So this is our first, second, third. So our nth, we'd expect to be n plus 1 squared. That's our nth term. We can view that as n squared plus 2n plus 1. If we took this pattern, let's say for instance this figure 3 here, I can break this down like this, and you should see this is a 3 square plus 3 more, plus another 3 down here, and plus 1 at the end. So I have my square, I have 2 of my term number, and I have 1 more. This pattern is very similar to the last pattern. You can see the only difference is there is 1 orange square been added on each time. So this is going to be our n plus 1 square that we visualized the last example, plus 1 more added on. Or we could say Tn is n squared plus 2n plus 2. Again, very similar. This time we have an orange one and a green one added on. So instead of plus 1, it's going to be plus 2. Here, if we look at the length and breadth of the rectangles each time, that will help us. So first of all, we've got a 1 by 2 rectangle in our first term. Then we have a 3 by 4 rectangle in our second term. Then we have a 5 by 6 rectangle in our third term. So if we're following the pattern, this is the same, but this is one more, this is two more. Okay, so it's not so straightforwardly obvious, but let's look then at our width. So we've got 2 is twice, 4 is twice, 6 is twice. So at least we know then that our nth term is going to be twice as wide. So then we look for a second pattern, and we can see here our height is 1 less than our width, 1 less than our width, 1 less than our width. So our height is going to be 2n minus 1. And so our general term will be 2n minus 1 multiplied by 2n, 4n squared minus 2n. If you look carefully at this pattern, you should be able to see that each time there is a rectangle with 2 squares added on, top and bottom. So every time 2 squares are added on top and bottom. This rectangle happens to be 1 by 3. The second one, 2 by 4. The third one, 3 by 5. With 1 square added on bottom and top each time. So we can expect our nth term to have a rectangle 1, 2, 3, so this will be n, 3, 4, 5, it's 2 more, so n plus 2. So our rectangle itself is n on n plus 2, but then we have 2 more squares to add to it. So our general term be n on n plus 2 plus 2 more, which is n squared plus 2n plus 2. Again, try to see the visual pattern. You should be able to see that each of these shapes has a square on the inside with 4 squares hanging off the outside. So initially we have a 1 square, then a 2 square, then a 3 square, so we should expect an n square. So overall our general term is going to be n squared plus 4 more. A 1 square, 2 square, 3 square, so we expect an n square plus 2 red ones to be added in. This is a 2 by 3 rectangle with a 1 missing. This is a 3 by 4 rectangle with 2 missing. A 4 by 5 rectangle with 3 missing. So we have a 2 by 3 with 1 missing. Then we have a 3 by 4 with 2 missing. Then we have a 4 by 5 with 3 missing. So our first term has 2, second term has 3, fourth term has 4. Our nth term we would expect to have 1 more, n plus 1 in that position. first term has 3, second term has 4, third term has 5. We're expecting n plus 2. We're taking 1 away, 2 away, 3 away. We expect to take n away. So we have n squared plus 3n plus 3, take away n. Our Tn is n squared plus 2n plus 3. And finally, the question, the puzzle at the end. So, Tile & Company specialises in multicoloured tile patterns. A small guest house is interested in the pattern below for its square-shaped reception area. How many tiles will be needed in total if the reception area needs 36 green tiles in the centre pattern? So initially we need to just look at that green tiles pattern in the centre. Initially we have 1 square, then we have 2 squared, 4, then we have 3 squared, is 9. So in our pattern that we're looking for, we'd expect there to be n squared. So coming up with our general pattern first for green tiles. So I'm just going to call this my green general term is n squared. I'm looking for 36, so I want that to be 36. So that in fact means that n must be 6. So if I'm visualizing this, I've got 6 by 6, or 36 squares here, so I have 6 along each edge. So I'm going to have 6 brown tiles along each edge also. And then I'm going to have 4 square tiles in the corner, white ones. So I've got 6 and plus 1 here and plus 1 here, 6 plus 1 plus 1, or you could say I have 8 times 8 is 64 tiles altogether.